To all of our viewers joining us, I'm so happy to have you back here again. And if you're new to the channel, then I hope you enjoy the content that we want to share with you. So today we want to predict the future value of gold in euros. And we want to see whether or not we can gain an edge by including alternative data from courtesy of the St. Louis Federal Reserve. Thank you. Of course, Fred, our boys, they got us on that. They have hundreds of thousands of alternative data sets that we will try dig into. Our rationale behind all of this is that hopefully we might uncover data out there that can help us in the markets. And as you'll see in today's example, we actually found some data, some very useful data from the Fred API that helped us reduce our error metrics and validation. But of course, we'll go through all the fine details. So without talking too much, if you're interested in checking out other data sets for yourself, I'll leave the link to the St. Louis Federal Reserve website, the Fred. It's a very simple API, very simple. You just need to create an API key and then you're good to go, for real. So you'll notice that today we're running from Google Colab. Yeah. It's due to the limited resources on this laptop. We were tuning a deep neural network, right? Because we have no idea the complexity of the function that's mapping the data. So we just went for a deep neural network, and then we were searching for parameters. So yeah, unfortunately this laptop won't keep up with us. So that's why we're running on Google Colab. But anyway, we started off by importing standard libraries, right? Pandas, NumPy, Matplotlib, Seaborn, right? Those are visualization libraries. And then we have stats models. We're going to use stats models for autocorrelation plots, right? The Fred API, of course, and date time. Yeah. And if you want to follow along, these are the versions of the libraries we're using, right? So standard shit. Anyway, here we were reading in the market data, right? So I'll show you the script that we used. It's all written in MQL5, the script that we wrote to extract the market data. You'll notice that my indexing is kind of weird. It starts at 96,911, or I fetched 100,000 rows of data. Well, I tried to fetch 100,000 rows, but there wasn't enough data, so it only started at from that point on. Yeah, so I just fetched all the data we had, and then obviously we set the time column as our index because we want to try and merge it in the next step. So we only wanted to merge on indexes, on timestamps that are common to both data sets. So after cleaning the data that we got from our MetaTrader 5 terminal, we now fetch data from Fred. So you're gonna need an API key. It's free and it's simple to get. You just create an account with them, and then you request an API key. Once you have that, you can call these functions Fred get series, and then the name of the series. So EVCLS. All right, let me see. There's also an app, you can get an app on your phone and check different time series, get notifications when shit gets updated. It's really useful. So I just want to walk through the dataset with you, the alternative dataset that we're considering. So CBOE, Chicago Board of Options, right? Yeah, Chicago Board Options Exchange, right? So that's where the St. Louis Federal Reserve are requesting this data from, right? You could read more about them. But really, yeah, it's one of the largest options exchanges. Like, it's a very large options exchange. I don't know much about options personally. Like, I don't trade options, but I know of them. However, we're more interested in the data, right? So it's daily data, as you can see, right? And it's not seasonally adjusted, which is fine. Our machine learning models can they can handle that. They are quite resilient these days. And then here we can read more about the data, right? So it's gotten from exchange traded funds, are shares of trust that hold portfolios of stocks designed to closely track the price performance and yield of specific indices, right? Okay, not much information about the data itself, right? But here there's a suggested citation, right, that you could go check out. ETF Volatility Index, and as you can see, they have a lot more volatility indexes that we can test for potentially more gains, right, in accuracy. And as you can see, it's really easy to use, and it's a lot of data, and it's free. Like, we can just download it and take it. But yeah, it's good to get a feel of the data first before we just start manipulating it algorithmically, because you don't want to be manipulating the data blindly. And as you can guess, GVCLS is a gold volatility index, also from the Chicago Board of Options Exchange. So we fetched our data, and the data had missing rows. We used mean imputation. Hey. Man, I haven't done these videos in a long time, bro. Yeah, as you can tell, man, I sound nervous right now. I don't know. My girl always tells me that, yo, you sound so nervous in your videos. Until I have no idea. But man, I hope you can follow my mumbling ass. Like, genuine. I'll speak up, huh? I'll speak up for you. Hey, it's late right now. It's like 1:26. But I told myself, nah, I'm gonna do this video before I sleep, because I've been telling myself I'll make a video, and then I never make the video, bro. You know how that shit goes. But anyway, we filled in all missing values with the column mean, right? Is that a smart thing to do? I don't know. I feel like maybe a rolling average of the mean might be better. God knows. I don't know. But that's what we did, right? So this is the step right here. All right. So from there, now we labeled the data, right? So the target is, of course, the future close price, right, of gold in euros, right? That's our target, right? We defined our forecast horizon, and then from there, we also created a binary target that's going to help us with plotting the data and visualizations, right? And then we looked at the data, like, this is what the data looks like now. So from there, we defined our predictors and targets, right? So the ordinary predictors that you would always get in the market, right? Like open, high, low, close. And then the data that we're getting from Fred, right? Our Fred predictors, a combination of the two predictors, right? The target and then the binary target. So now we're looking at a correlation heat map between the predictors. So as we could, obviously, like, this is pretty standard. Prices always has like very strong correlation with itself. That's why we're seeing this first block of ones. And then as you can see, there's very quite poor levels of correlation between our alternative data and price. However, there's quite strong correlation between the two alternative data sets. Like, so as you can see, it's positive 0.41. However, correlation doesn't always imply that there's bound to be a relationship inside the data. Correlation could simply be emanating from a common effect, a common participant in both markets, a common cause that's affecting both of these markets, could be an alternative explanation for the correlation being observed. You know, we tend to just jump to conclusions. But anyway, it's nothing earth-shattering, right? We tried to look for visual relationships within the data, so we plotted the gold volatility index against the close price of euro gold, and yeah, nothing. It really looks like there's no very strong discernible relationship, except for this when the gold volatility index like approaches these highs of like 35, like we tend to see almost exclusively bullish action here, right? So that might be worth looking into, right? Yeah. However, then again, we also need to consider that this is not the entire time series data, right? This is just a sample. So it may not be representative of the true relationship, but from the data that we have, these are some of the reasonable deductions we could make. I don't know. And then, oh, sorry, I almost forgot to mention. Notice how we have this, it's almost like a stick right here in the middle of the data. Yeah, those are the mean imputed values, right, that we put in the data early on. You see it? Yeah. We're going to observe that again in our next plot. So there it is again, our little stick of mean imputed values, right? And again, we see hopscotch patterns, right? We see overlaid bull and bearish price action, like in and around the same price levels and the same volatility levels for the euro index this time. However, again, we notice that when the euro index like approaches these extreme highs, right, and it appears that for oh yeah, I probably should have standardized the scale. In retrospect, that may have helped, like, so that like you know, we have, it's 1 standard deviation from the mean, 2 standard deviations from the mean, but whatever. We notice that like when price levels approach these highs, we tend to see almost exclusively bullish action. However, then again, consider small data sets, not entirely representative of everything that's possible in this market, but I don't know, it appears pretty strong. And then here now, we created a scatter plot using the 2 predictors themselves, these 2 alternative data sets. And on this plot, it's that effect appears very strong, like it appears well pronounced now. Like these are the type of relationships that we look to exploit, right? Whereby there appears to be you know, I hate to say this, but like a natural boundary. I hate saying it because like there are high frequency trading algorithms out there that are just making decisions in milliseconds. To call it a natural boundary sounds like a misnomer. However, I think you can see what I'm trying to say, for lack of better words. It appears that like once the gold volatility index, right, crosses this boundary from 30 to 35, oh my god, right? But I don't know. Anyway, remember, it's daily data, right? So like what, 3,000 days, right? Isn't we have 3,000 rows, right? Like after we merge the data, let's just look at that. Yeah, 3,067 rows. All right, that's a long time, right? It's a long time. A couple of years, right? We plotted the data in 3D here. We thought maybe the effects might not be visible like in just 2D space. You could kind of see those regions that we're talking about, these ones right here, whereby we just observe very strong bullish action. There appears to be small clusters here of like bearish zones. However, this is a bad example because here they're somewhat clustered and that might be challenging to separate. But this zone right here, it's the first thing that caught my eye. I don't know. Maybe I'm overlooking something, right? Or maybe the sample space is too small. From there, we could also try a T-SNE plot. A T-SNE plot, right, tries to represent high-dimensional data in low-dimensional space. And without diving too much into the complexity of this algorithm, because it's complicated enough on its own, that's what it's doing. And it has a cost function that it evaluates using gradient descent to try and measure how well it's representing the data in higher dimensional space. So yeah, it's some pretty clever shit. However, due to the nature of the underlying optimization algorithms, if you run these T-SNE plots, right, repeatedly, you'll get slightly different plots each time, right? That wouldn't be strange to see. However, with T-SNE plots, we're not necessarily paying like all our attention to the exact, curvature of the plot. No, really, what we want to see is whether the algorithm can identify clusters that, like for example, it might be able to separate some of these clusters for us in ways that we may not be able to identify. And when we created our T-SNE plot, these are the results we got back, and it appears right, like visually it looks like a family of snakes or something, right, or like slugs, right? Visually, like however, that might be serial autocorrelation that we're seeing, right? Like dependencies across time that are creating these long streaks. And I don't know, there appear to be somewhat distinct clusters here, right? So there's definitely a relationship here that's evolving over time. The question really is like how do we expose that relationship in a meaningful way, right? That's really like the problem we're trying to solve. We created autocorrelation plots, right? Like from looking at this, we could tell that there are definitely dependencies across time. Possibly. So yeah, we looked at the autocorrelation plot, and as you can see, it's a very strong tail, a heavy tail, right, across the close price of gold and euros, right? And so how do we need all those lags though? How much new information is being carried across the lags? This just tells us that like price appears to have very strong correlation levels with all its past predictors, right? But then when we now look at the partial autocorrelation, we see that like really only the first two lags account for most of the correlation we observe like across all those lags. So possibly these two lags could be, good predictors that we could try, right? That's what the data appears to be suggesting to us. And then we perform the same again with the same plots. This time we're using the Euro Volatility Index. We're looking at its correlation levels, right? And it has a falling tail, right? Oh, sorry. Another thing. Hey, if you know a lot about autocorrelation plots, please feel free to like help us interpret this plot. I mean, hey, at the end of the day, we're all just trying to make sense of the world around us with the information that we have, right? But I believe when you see autocorrelation levels this strong, it might suggest that difference in the data would be helpful. But that was really necessary when you're dealing with like legacy models like, ARIMA models, right? And these days with deep neural networks, like, those are problems that our grandfathers had to deal with. But hey, let's move on. Looking at the partial autocorrelation again for the Euro Volatility Index, this time we see that it doesn't fall that fast. So some of these lags might be important, right? I forgot to explain, this blue cone is a confidence interval. So lags above these confidence intervals are considered significant. Gold Volatility Index, again, the autocorrelation plot, again, looks very similar to the Euro Volatility Index. And we see that it's kind of oscillating. I don't know if you can see that. It's kind of got this sine wave structure to it. Almost, it's barely there. It's barely above the confidence levels, but those might be seasonal effects. That might be caused by seasonal effects in the data, right? And again, we see that, it appears that like the first 5 lags might be quite significant. They account for a lot of the correlation we see in the data sets. Okay, that's interesting. That's good to know, right? So now we move on to, we want to start preparing our data so that we can model it, right? We're going to be using a deep neural network, right? 2 stacks, right? 2 hidden layers. The first has 20 units, second has 5. So the first thing we did was reset the index for our data, and then we created like the predictors and the targets, right? Dedicated data sets, and then we scaled our predictors using a robust scaler. From there, we performed train test splits. As you can see, we have three different splits, okay? So the first split uses ordinary market data, open, high, low, close, right? Quotes on gold and euros. We're not shuffling these data sets. Please, for the love of God, do not shuffle time series data. Bro, I don't want to start ranting. Okay, I don't want to start ranting. It irks me when I'm watching like someone do a machine learning tutorial and he's shuffling times. I'm like, dog. But anyway, and then they crack 90% accuracy and they tell you how it's so easy. And you're like, no, it's not fucking, bro. It's not that fucking easy, okay? You can't just shuffle time series data and then tell me it's fucking easy, okay? No, man. Like, there are people like investing a lot of time into cracking this, okay? We're not fucking playing around, bro. Take that shit back to middle school, fam. That's where your model belongs, okay? Don't shuffle, please, for the love of God. Train size, half. Test size, half, okay? So the train half, right, will be used to optimize the model. The test half is going to be used to test for overfitting and to validate the models that we have. We are not going to shuffle the data at any step. We're going to use 5-fold time series cross-validation. You can't use leave one out cross-validation in time series. Again, that doesn't make sense. It doesn't make sense because think about it. Okay. Anyway. Oh man, I'm getting notifications. I'm sorry if you're playing that loud and like, yeah, but anyway. So now we create our time series object, right? Okay, there we got it, TCSV. And then we create a data frame to store our validation error, right? And then we're gonna have 3 columns, right? So the first column is going to store our MSE, right? Using ordinary predictors. The second column is gonna store our MSE using the Fred predictors. And the third column is going to store our MSE using all the predictors. So, spoiler alert, we got the lowest error using all the predictors, right? Okay. We got the highest error using just the Fred predictors, and using ordinary market data was in the middle, right? So it appears that like the alternative data isn't quite informative on its own, and the ordinary market data is more effective when you have alternative data. So together, together, hey, we crushed that shit. No cap, bro. So let's see. So now here we're performing cross-validation. As you can tell, I kind of did this manually. So what I was doing was I'd come here, right, and then I manually went through each column, dog, because I also had to like change the predictors, right? So as you can see right now, we're using the final set of predictors, like, so that's train X that has all the predictors, and it goes in log 2, right? Column 2, the last column. So yeah, for column 1, I went there and then, open, high, low, close, train X. Like, if you're gonna be repeating that, you should know that's how I did it. So this is our validation error, right? Huge ass fucking numbers. Don't even try to read that, bro. You're gonna make a mistake. Trust me. Let's just look at the mean, right? Let's look at the mean. And then what I did was I used the mean performance of the model that we have that's using open, high, low, close data, right? And then I subtracted that from all 3 columns. So by doing that, the difference between it and itself is 0, right? So that's our baseline. Oh shit, you can't see that on the screen, sorry. That's our baseline, right? Open, high, low, close predictors. That's why there's nothing. It's exactly 0. And then the Fred predictors, as you can see, it's greater than 0. So that means that model, it had higher error levels, right? And then all predictors is negative. It's less than 0, as you can see. So the difference between, so yeah, we're just plotting the difference between the models, because when you, anyway, you get it. You get it. It's just a different way of looking at the data. So this clearly shows us that like our best performance came from using all the predictors that we had. Right, and then now we can look at the standard deviation, right? This is quite interesting for us because the tighter the error levels that the model is producing, right? That's a demonstration of skill. That's more certainty. So as you can see, our standard deviation when we're just using ordinary price data was ridiculous, right? This guy was right, and then he was dead wrong, and then he's all over the place. And the Fred predictors actually had very low variance, right, which is good, but then they had high error rate, which means that they were consistently bad, right? So, and all predictors, it's somewhere in the middle, right? It's acceptable. And when we look at box plots now, that's like a visual way of everything we've just checked. We could have just looked at one box plot, but we went through everything anyway. As you can tell, the mean performance when we use the all predictors, there it is, right there, it's the lowest. And then the mean for the Fred and ordinary data is quite high. The distance between these two whiskers, right, like the variance, as you can tell, it's less variance than what we get here. Like, here you can, you're all over the place. This one, but then it's pretty tight, but then it's consistently high, and then that's the problem. So now we want to try understand our model like a bit better. So we're going to use Alibi, right? This Python library called Alibi, in order to get explanations for our model and what our model has learned. So using Alibi, we're going to be looking at the accumulated local effects. So accumulated local effects was suggested in a beautiful research paper, right, recently. And when I say recently, I'm talking on a relative scale. Like, there are some techniques that are very, very old, right? So yeah, AO is quite a new algorithm. And it really shows us the change in the targets. It helps us understand how the target change in response to changes in our predictors. So if there's little or no relationship, right, between the changes in the target and the changes in the predictors, right, for that particular plot, the AO plot will just be like a flat line, right, showing that like the target is not sensitive to this particular predictor. However, as depending on the nature of the relationship between the target and that particular predictor, the AO plot starts to deviate from a flat line, right? So it can also help us like observe if the relationship appears to be convex or non-convex, right? These are the type of things that we can infer from these AO plots. So we start off by initializing our model, and then we train it again on all the data that we have, right? And we create the AL explainer, right? So this is our deep neural network AL explainer, right, on the model we just fit. And then here we obtain an explanation. So first we convert the data to NumPy, to a NumPy array, and then from there we get an explanation from the deep neural network explainer that we created. And then now we call the plot AL function, right? And then we tell it, since we have 6 predictors, we're gonna have 3 columns, right? 2 rows of 3 columns. And then here we're simply specifying the dimensions of the plot. And share Y, you know, now that I think about it, we could have set that to yes. Yeah, we definitely could have set that to yes. However, this is our AL plot. And as you can see, the opening price, right? It appears that the target like starts becoming less sensitive to the opening price. Past a certain point, our AL value just flatlines there, right? It's not changing by much. And we're observing the same thing, that like it appears to be losing sensitivity towards our predictors, right? As it's moving on. However, our Euro volatility index now, as you can see, it appears to our target appears to grow more sensitive to it, right? In the opposite direction. So this, in a sense, maybe this is why this particular data set, a combination of this data set, appears to explain more of the variance in price than just using price alone. Because as you can see, it fills that void of sensitivity that we're constantly losing with these predictors, right? Like just look at the close price. It looks like a hockey putt, right? So beyond this point, right, which is, you know, if you really think about it, that's a huge section of the graph, right? It's a huge section of the graph whereby the changes in these predictors doesn't really explain any of the changes that we're seeing in the target. But our volatility index now, it appears to be coming to save our asses right here. These are the type of explanations that the AL plots can help us get, because, you know, we're trying to understand a deep neural network. So it helps us observe what type of relationships our model appears to have learned. So now we're also going to consider Shapley values, right? SHAP values. So Shapley values help us observe global importance in a model. And they can also give us local explanations, right? And by local explanations, I mean explaining a particular prediction. So in our current setup, we want to get global explanations for our deep neural network. So we want to know which predictors do you think are important, right? And our SHAP calculations are suggesting to us that the market data itself is the most important, and our volatility indices are not as important as the market data, right? According to SHAP. However, they account for some quite a lot of variance. And again, as was being suggested by our AO plots, it seems that our Euro Volatility Index, it explains variance in parts of the target that we were not able to explain before. So now, of course, I'm talking about the output space of our target, right? When I talk about part of the target, but anyway, now we want to tune our model. So we're going to perform this tuning in a two-step process, right? First of all, we're going to randomly search the parameter space, right? Because I mean, hey, these brute force searches are not always possible, especially like when the parameter space is large. So first, we're just going to initialize the model, right? Again, 20 by 5 layer. And then from there, we're going to define our tuner object. So first you pass the tuner object, the model, right? And then from there, we define the parameter space that we want to search and the possible values, the accepted values for that parameter space. From there, we're defining the total number of iterations, whether or not we want to use cross-validation, right? The number of jobs and score. Oh my God, right now, now that I'm walking through this with you, I'm asking myself, does scikit-learn shuffle the data? There is no parameter for shuffle. There's no shuffle parameter. Oh my God. Cross-validation generated default. Now determines the cross-validation possible inputs. None. To use the default CV integer, CV splitter, an iterable train test. For integer, non-inputs, if the estimator is a classifier and y is either binary or multi-class, stratified k-fold is used. In all other cases, k-fold is used. The splitters are instantiated with shuffle equals false. Okay. Thank God. Oh my God. Okay. No, we're good. We're good. So at the time of recording, scikit-learn are not randomly shuffling this data set, which is good, which is what we want. Setting n jobs -1 so that we can perform the tasks in parallel. Thank you, Google Cloud. Scoring negative mean squared error, right? Because we want to minimize our training error, right? And then from there, we fit our tuner and we can see the best results that were found. So the tolerance level, right? And as you can see, this is the best results we have found. Now, you're a smart people. You can read that for yourself. If you need me to explain anything, like we can walk through it, But anyway, these are the results we found. Now, I also wanted to visualize them, So we created a data frame and then we defined our 3D plots. And I should have seen this coming. I feel like an idiot. But of course, right, it's randomly searching in a fixed space. So most of the points overlap and then they are just slightly above each other or below each other. But as you can see, our minimum point must have been somewhere here, right? That must be our minimum error. Right, all right. So like we said before, our optimization process is going to be two-step, right? So first we're going to randomly search the space. And then now we're going to use the endpoints of our previous optimization step, right, as the starting points for an even deeper search, right? using SciPy. So we're going to use the minimize module from the SciPy optimize library, right? And we're going to be using limited memory Bernoulli Freudian Goldfarb channel LBFGS algorithm to try minimize our cross-validation error, right? Fivefold cross-validation on the training set, right? All of this is being done on the training set. So we import the libraries and then we create a data frame to store our accuracy, right? So it's gonna have, right, again, five indexes, and we're gonna have a column for our current error, right? Because we're cross-validating. And then now we're gonna define the objective function, right? So the objective function is gonna take an array called X, right? This array is being passed to us by the SciPy library, and it contains the new inputs that we should test. So as you can see, we define the neural network, right, by first using the best parameters we found, right? Shuffle was true, right? That's what our random search learned. And then from there, alpha and tall, right? We're going to try to optimize that just to try squeeze out as much juice as we can. And then from there, we cross-validate the model, right? We fit the model onto a portion of the train set and then measure our root mean squared error on the remainder of the training set, right? So that's the test indices still on the train set, right? We're not going to use the test set yet. So from there, we define the starting point of our optimization algorithm, right? Remember, these are the endpoints of the previous step. And then we define the bounds, right? Because if you don't define bounds, the SciPy library might throw negative inputs at you and you're going to fail to fit the model, right? sklearn is going to throw errors back at you. So yeah, define your bounds. You got to be careful with the bounds though. You can't just define them how you want. You really have to read the documentation, because if you allow it to go beyond the bounds, trust me, I've made the mistake more than once. I'm probably going to make the mistake again. But hey, it's only frustrating when you don't understand the mistake you're making. Like that's when shit is frustrating. But then once you learn that, oh, yeah, so yeah, watch out for that. Here we run the minimization procedure, right? So our objective function, remember, it's returning the cross-validation error, the starting point, right? The optimization method that we want to use, and the bounds for our optimization, and then that's going to return us, right, an optimization object from SciPy. So, yeah, it would be cool to look at like the results, but then let's just test for overfitting one time. Like, hey, man, who cares about like all those results if we're just overfitting, right? Okay, and spoiler alert, we were overfitting. Okay. Our best performing model was the customized model, this one in the middle. We outperformed the default model, but the LBFGS model was simply overfitting. It produced higher error rates. So we loaded all three models and then we had put them in a list, right? So we can iterate over them. And then we created another data frame to store our validation error. And then we reset the indexes. I did it again. Okay. I'm back. We reset. Man, I feel like I even made that error in spelling indexes. But then again, hey, we reset all our indices, right? And then from there, we fit each of the models on the training set entirely, right? Because now we're going to be testing them with the test set. And remember, this is the first time the models are predicting on the test set. So we iterate over the models, and then we fit the model on a portion of the test set and then test it on the remainder, right? Normal time series cross-validation. And again, these are validation error levels. Now, unlike the last time, this time you can clearly see that the values this side appear smaller than the values, because here, oh my God, we're getting really large values, right? However, like I said, let's just look at the mean, right? Once you look at the mean, it all becomes obvious, right? Now, an argument against this data, well, it's just five folds. So these could be two outliers that are probably skewing our understanding. However, 5 series cross validation it's pretty standard. We could have done 10, right? I don't know, but I feel like 30, like if you're paranoid like I am, 30 would be best. I don't know. But hey, so the data appears to be suggesting to us that we were overfitting with the LBFGS model, and the customized model seems to be somewhere in the sweet spot, which is crazy because that was a random search, right? But hey, again, we did the same thing. We're plotting the difference, not just the mean itself, but the differences between the mean. So the error of the default model is the 0 line exactly. And as you can see, both models have negative error values, which means that they were performing better than the default model, right? Which we saw in the mean, but it's the same information. Just another way of visualizing the information. Again, standard deviations, and then I subtracted, and as you can see, the customized models had lower standard deviation values. So that means they were consistently producing better results, right? Which is what we like to see. That's a demonstration of skill. When we now visualize the plots, you can clearly see, it just went to the moon. It went Elon Musk, Tesla, right? I mean, SpaceX, right? Look at that. That is astronomical. And as you can see, our customized models, they appear to be better behaved, right? But then again, this is over just fivefold. So we might be getting too excited. But then again, when we visualize box plots, it's like, whew, goddamn. Man, you can clearly see the difference in performance. Our customized models look like pancakes. And our default model looks like we're trading, it looks like the actual chart itself, doesn't it? Quite thick, a lot of variance, very high error levels. It would be reasonable not to use the default model, right? It would be reasonable not to. So from here now, we want to prepare to export our data to Onyx format so that we can use it inside an MQL5 export advisor. But before we can do that, we have to standardize and scale the data in a way that we can reproduce in our terminal. So yeah, we perform this is a very standard pre-processing step. Subtract the mean and then divide by the standard deviation of each column, and yeah, store those scale factors, write them out to file, right? Which is what we did. We wrote the data to file, and then we were reading it in our MetaTrader 5 terminal. So that way, whenever we fetch new data, right, we can repeat this process precisely. So from there now, of course, that's how the data looks like now, but that's not interesting. So now we want to export the data to Onyx format. So if you haven't heard about Onyx, right? Onyx stands for Open Neural Network Exchange, and it allows us to build and share AI models in a way that is language agnostic. So you can build a model in Rust, right? I don't know if Rust extends support to the Onyx API, but if it did, you could build a deep neural network in Rust, and then I could use it in Go, right? If Go supports Onyx. So yeah, that's the big picture with Onyx. And then we're going to use another library called SKL to Onyx, right? Scikit-learn to Onyx. And it helps, it's a wrapper built for like converting scikit-learn libraries to Onyx format. I find it really straightforward to use. It's, oh my God, it's nah, bro. It's nah, trust me. So we fit the customized model on all the data we have now, right? And then define the input types. This is very important because the input types are not always easily accessible, right? So you might lose the input types. You might forget what type of input it was, right? So yeah, define the type so that you won't have problems in like in future down the line. And then from there now we create an Onyx representation of the model, right? So convert sklearn, and then we pass it our customized model, the input shape, and then the target offset is 12. Now, there are so many different target offsets available. I don't know the difference. I won't even lie to you, bro. I should probably sit down and read that. Maybe there are functions like I'm not taking advantage of. However, bro, I don't even know. If you know what those target offsets mean, man, holla, tell me, like, how could we finesse that? Like, you know? But anyway, now we save the Onyx model, and it's really easy. You just define the name of the Onyx model, and then you pass the Onyx library, right? From the Onyx library, we're gonna call the save model function, and then we pass it the Onyx model and the name of the model, and then it's written to file as an Onyx file. From there, we create a function that will write out our alternative data to CSV format, right? So this function is going to go fetch the data from Fred, fetch the last row from the data, create a data frame, and then write that out to CSV format, right? And then we now create a loop, an infinite loop, right? That will go fetch the data, write it out to CSV format for us so that we can read it in. As you can see, right? I've included the path to my MetaTrader 5 terminal. Of course, I've commented it out now because, you know, this right now, I was running this on Google Colab, like so that I could quickly optimize. However, enter the path like to your files so that the function is writing out to files for you. And then once we've done that, right, we are now ready to come here to our MetaTrader 5 terminal. So here, the first thing that I'm going to show you is the script that we used to fetch the data that we needed from the MetaTrader 5 terminal. So the data on the euro gold market, the gold euro market, right? So once we have that, we're now ready to start building our expert advisor. Man, right? Yeah, dog, it's 2 a.m. Like, if you're still with me, if you're still kicking, dog, like, let's go, man. Like, ew, I don't get tired, honestly. I don't get tired, bro. So the first thing we do is that, yo, can you hear my girlfriend snoring in the background? And then she tells me that I'm the one who snores. Can you hear that? Bruh. Anyway, so the first thing that we're going to do is require the Onyx file, right? So we're going to require the Onyx file as a resource. That way, when we compile the program, right, the Onyx model is included in the compiled program. So remember, we saved it in our files directory, right? And then gold, euro, Fred. Remember, it's daily data, right? .onyx. Okay, dope. And then from there now, these are the libraries, right? The trade library. We need the trade library for opening and closing positions, managing our positions, right? Getting our profit, right? All that good stuff. And then now, here we have global variables that we're going to be using. So this is obviously going to be our Onyx model, right? These are the mean and standard deviation values that we saved earlier in our scaling factors, right? And then these are the model inputs and the model outputs, right? Okay, dope. This is the bid and the ask price, right? And then this is going to store the system state and the model state. Now, this is going to help us detect possible reversals, right? Like, if you've read my articles before, then I don't think this logic should be anything new to you. But then anyway, if the model predicts that price is going to appreciate, right, we're going to store a flag, right? We're going to mark it as like 1. We're going to set model state to be 1. And then when the system now takes that buy position, the system state also becomes 1. But then when the model now predicts that price will fall, the model state will transition to -1. But the system state, right, is still going to be 1 because we haven't changed it yet. And then when the system now, when the flag is now tripped, right, when the system state and the model state are no longer matching, we close our positions because, you know, the AI is suggesting that like price might retrace and we don't want to take those chances. So the first thing we do when initializing our expert advisor is that we're going to try load our Onyx model, right? If we fail to load our Onyx model, right, we're gonna halt the initialization procedure and just, you know, cancel. We don't proceed because we need the Onyx model. We can't proceed without the Onyx model. Furthermore, if we cannot load the scaling factors, right, again, we're gonna halt. We're going to terminate initialization because there's no point having a model if we cannot scale and standardize the data, right? Our model is going to give us incoherent predictions if the data is not scaled. And then otherwise, if nothing goes wrong, then we oh my God, we failed to load our model. No, we managed to load our model. Okay, there we go. Upon deinitialization, what we're going to do is we're going to free up the resources we no longer need, right? Don't worry, we'll look at these functions like one by one. But you can kind of guess what this function is going to do. This function is going to release the Onyx model and it's going to remove the expert advisor, right, to free up the resources. And then now on each new tick, right, the first thing we're going to do is we're going to fetch market data. So remember the bid and the ask variables that we defined earlier. This function is going to update them. From there, we fetch a new prediction from our model. Once we have a new prediction from our model, if we have no open positions at all, then we will follow our model's lead, right? If the model suggests that we should buy, before we do that, we will check on a higher time frame. Oh my God, I just realized something. I wanted this to be weekly data, not daily. I wanted to check on a higher time frame. I can't be checking on the same time frame. Hey, no wonder it probably entered a stupid position. But anyway, man, making these videos is so helpful because I get to read through the code again one more time. So yeah, what we're gonna do is we're gonna check on the week, right, on the weekly data, to see if we're also in an uptrend. So we're gonna look back like 12 weeks, right? That's about 3 months, which is one business cycle. So if the institutional players have been appreciating prices for that long, then yeah, maybe it's worth it. Maybe it's a high probability setup. And same thing on the converse side. If the model has been suggesting that we sell, first we're going to look over the last business cycle. And if price levels have been depreciating over the last business cycle, then hell yeah, we'll take a bet. Oh my God. Do you see that? I called trade.buy twice. Yeah. Man, okay. I am definitely going to continue making these videos. Yeah. This is so helpful. Look at that. I'm trying to sell at the ask price. Anything else I missed? Appears good. Okay. Anyway, Man, you know how it is, dog. Bugs are everywhere, bro. But hey, we try to get every last one, huh? So if our model wants to sell, again, we're first going to look at the changes in price on higher time frames, and if they permit us to sell, we will sell. Right? So that's the model predict function. And also remember, we're storing the state of the system, right? After doing so. And also, like after we buy, the system state becomes 1. After we sell, the system state becomes -1. And then if we already have positions open, oh my God. If we already have positions open, right, then we will manage them. If the model state is not equal to the system state, then we will close our positions, right? Quite simple. So now this is the function that is going to fetch predictions from our model predict, right? I'm trying to emulate sklearn, right? So this is the function that's going to fetch our predictions. So the first thing that we're going to do, we're going to iterate through a loop, right? Remember, there are 6 values that we need, right? In retrospect, now that I'm reading this code again, I don't know why I did that. I could have just but anyway. The first 4 inputs that we need are going to be fetched directly from the gold euro market. So we're simply going to create a matrix, right? We're initially going to fill it with zeros, right? Just 1 row, 4 columns, and then we're going to copy the rates, right? Daily data on the current symbol, because the current symbol will be gold euro. We're going to copy rates open, high, low, close, right? And then 0 is the start index. So we want the most recent data that we can get, and just 1 row will be fine. That's the amount of data we should fetch. From there, we're going to fill in the data, right? And we're going to perform the standardization that we did before. So it's a good thing we saved those mean and standard deviation values. Again, subtract the mean, divide by the standard deviation, right? I wrapped all of that in parentheses. And then from there, man, had to get a good stretch in. From there, we cast the data to float type, and then we stored it in our model inputs. And once we got open, high, low, close, right, the first 4 rows, we then called the read Fred data function. And this function is going to go fetch our Fred euro CSV, right? Our Fred gold euro volatility indexes, right? It's going to try read that file, validate that it has read the file, right? And then from there, it's now going to continue reading in the file. So first we create a counter, and then the current string that is being read. And shout out to my boy Omega. Like, shout out to Omega. He really helped me, like, with this code right here. Let me just no, for real. Omega deserves a shout out. Man, Firefox is tripping. Anyway, my boy deserves a shout out, Omega. Like, yo, bro. Learning. Like, let me just show you. My boy. Where is he? Failing to read a CSV file. Man, if you're looking for someone who's really helpful, trust me, Omega is a really helpful member of the community. My boy, shout out to the boy. The boy is the plug. The boy is the plug, for real, man. He's got products that you should. The boy. My products are free. By the way, if you're also looking for products. Yo, but shout out. My boy, very helpful. He put on with the code. But anyway, we read in the data, right? After reading in the data, again, we performed the same standardization step. Subtract the mean, divide by the standard deviation values, cast it to float, right? And in this particular case, we had to cast twice because remember, our value was initially a string, right? And then the final thing needs to be casted to float, just to be sure. You know me, I'm paranoid, bro. I'm paranoid. And then from there, once we have our model inputs ready, we then fetch a prediction from our model using the Onyx run function. And then we pass it the Onyx model, we pass it the default parameters, the model inputs, and then a vector where the output should be stored. Comment the model forecast, give the user feedback, right? And then if the model output is greater than the current close, the model state is 1. Otherwise, the model state is -1, right? So this is how we keep track of whether or not we should close our positions, right? The AI will help us decide whether we should close our positions. Otherwise, if we end up in this section of the function, then that means we failed to find the file. And yeah, at least it's not going to fail silently. This function, as you can tell, is going to fetch our market data, right? It's going to fetch the current bid and ask prices, right? Pretty standard stuff if you've learned MQL5 before. This function is going to free up the resources that we no longer need, right? In the deinitialization step. So it's going to release the Onyx model and it's going to remove the EA from the chart, right? And it's also going to give them like a thank you message for using the volatility data products. You know what's up. Our scaling factors here, as you can tell, I hard coded them, right? The reason I chose to hard code was that, look at this. Okay, if we were to write code to read in that CSV file, we would write more lines of code than what it takes to just hard code them. And so I was like, nah, that's not worth it. Also, the mean values and standard deviation values are not going to change. Like, we're not going to change them ever again. So you could hard code it. From there, I just did a check to validate that the values were actually stored in memory correctly. So the sum should be greater than 0. Otherwise, if the sum is not greater than 0, like the sum of both those vectors, then something went wrong. From there, we also define a function to load our Onyx file. So this function is going to first create the Onyx model from the buffer we loaded earlier, right? So it's going to create the Onyx model from the buffer with the default parameters. And then from there, we're going to validate the model we just modeled. Man, the model we just created. We're going to validate the model we just created. And if the model we created is invalid, then we're going to give the user feedback that, yo, the model is invalid, bro. And we're going to return false, which will halt initialization. But then if we don't return false, then from there, we're going to attempt to define the input and output shape of the model, right? And then we're going to validate the input and output shape. If that fails, then we're going to give the user feedback that we failed to define the input or output shape. Otherwise, we return true. And that is everything put together. And this is the result, right? So as you can see, the model is trading right now. It's making a loss of like $8, right? However, remember, we made some mistakes in the code, and now that we fixed those mistakes, let's just close that position and let's compile this one more time. All right, let's compile this one more time and see. Let's see what difference that makes. Wow. Now it's not opening positions. Okay, let's see why it's not opening any positions. Oh, it opened a buy again. Okay, let's see why it opened a buy. So as we can see, the model is forecasting that future price levels will reach as high as 2,284, which is an increase from where we are right now. And then if we look at the data on a weekly time frame, as we can tell, we've been going up on the week, right? Oh my God, since 2023, the price of gold has been appreciating. So it seems that institutional players. Oh my God, bro. But I mean, this shouldn't be shocking because we live in a fiat currency world, right? Like, money is constantly being devalued, right? So, currency does not store value. So this chart shouldn't be surprising. But as we can tell, institutional players are clearly pushing up the price of gold, and the model also wants to take a buy, which is what we would expect. So if you've watched this video this far, oh my God, thank you so much, bro. I hope I was helpful, huh? And until next time, man, I wish you peace, prosperity, and profitable trades, man. Huh? I'll keep you updated on how this trade goes. I won't switch off the laptop. I'll leave it running. Let's see what it does. Alright.